So this week is all about theories of failure. In the previous week, we learnt about beams and the properties of beams. We also saw and defined that a beam is a versatile structural element. We came across few examples for supports of beams. There was also an overview on loads that are acting on beams and types of loads. We learnt about BMD and SFD, which is basically bending moment diagrams and shear force diagrams. We also solved few problems relating to them. Later, we came across concepts like bending and deflection. We also derived few formulas relating to bending and deflection and justified it with examples. And finally, we concluded the last session with torsion and its formula with a suitable example. Now, this week, the table of contents is as follows. First, we'll be looking at failure by yielding and fracture. Then we'll go through ductile and brittle materials. Next, we'll be seeing about yield criteria for ductile materials. And then that will be followed by failure criteria for brittle materials. And we'll end the course with a suitable example. Now we can go into the course. Let us go into the first topic, which is failure by yielding and fracture. So in applications, failure is defined by the physical situation. Sometimes, as an engineer, we have to understand what failure is and how we can define failure for certain applications. At times, a small amount of elastic deformation can be considered as failure because it's crossing the yield stress. Whereas, for certain applications, permanent deformation will be considered as failure because it is going into strain hardening, necking, and other aspects. And sometimes, in certain applications, we have to wait till fracture to define failure, and this point is very application oriented. So first we have to define which type of failure we will be taking as our case to approach this problem. If you see the figure on the right, for ductile materials, there are three phases. Plastic deformation, as we have already seen, the first zone, which is yielding. The second phase is necking, and the third phase is called fracture. And these phases can also be called as yielding, strain hardening, necking, and these three actually comes before fracture. So therefore, for certain material applications as engineers, we always ideally want it to be lying within the elastic limit because this is where all our equations can work properly, which is basically the proportionality limit. And with that, we don't want the material to go beyond the elastic limit, which will basically make it a plastic. There are certain applications where even a little bit of elastic deformation will not be allowed. For example, we can take concrete. So concrete has a very small amount of elastic strength, or we can also call it as tensile strength. So hence, the elastic deformation in the tensile zone is something we shouldn't take as a complete value. However, there are some applications for which we can go a little bit into the yielding zone and we can still make that material work. But as engineers, again, we want the failure to be defined at the yielding stress, which is a point where the yielding starts just before the yield point. So we have yield stress now, and with the use of factor of safety, we can make sure that the material doesn't go into fatigue under its normal lifespan. So now, an application's failure is defined by the physical situation of that application. We will compare stress applied to an object with its limiting stress. And when we take a brittle material, as you can see on the right side, very little yielding is experienced and the tensile fracture will typically hold very large amounts of compressive loads. In the same time, tensile load cannot hold it. So, finally, to sum it up, any material is said to be experiencing failure only when it goes into fatigue, which is when it breaks. So, with that, we can see the common types of failure. Failure in a material can be perceived as the aspect where the material experiences fracture. Now, this is also known as the complete separation of the material into two parts or many parts. Another reason behind failure may also be attributed to excessive deformation, both elastic and inelastic, due to repetitive loading or various other reasons. So, as we saw, there are different types of failures with different types of definitions depending on the application or depending on the material. But finally, the most common types of failure are of three types. The first one is excessive elastic deformation. Second one is yielding failure. The third one is fracture. And as for excessive elastic deformation, this deformation is accompanied by different failure modes. So, these failure modes can be stretching, bending, or twisting, buckling, and vibration. Now, these aspects, although are called elastic deformation and it is known to recover, but in practice, this material never recovers. So, usually there is a very small amount of deformation. Every time a load is applied on a system, there is a very small amount of deformation. And because this deformation is very small, it doesn't really affect the performance of the system, and therefore we term it as elastic deformation. And as a result, we can expect that the material will not fail due to that elastic deformation. However, we all know that there is a particular lifespan for materials and there cannot be any material that stays forever. At one point, it will need to be replaced, changed, or at least serviced. So, even with the little amounts of elastic deformation, every time it is given, the amount adds up. And this accumulation results in huge amount of deformation. Now, with that, stretching, bending, or twisting are basically common types of failures. Now, any material can undergo constant stretching and bending. So, for example, if we take a screw and if we keep twisting the screw for a couple of years, we might notice that there is a problem with the threading of that screw. Now, to repair the screw, we again take it out and then we'll try to repeat the threading process using some other machine on this screw. Now, again, if we keep repeating this threading process on top of that screw or along the screw's axis, then it's going to experience repetitive loads, and due to this, the screw will attain failure. Now, obviously, this is a very common type of failure that the screw will be undergoing, and that comes under stretching, bending, or twisting. Another mode is buckling. Buckling is again a very common but a very important phenomena when it comes to beams or columns. Even though the material is not failing with the loading system, but if there is an actual load, then there is a tendency that it might buckle. So, as engineers, we'll have to make sure that the loading does not result in the buckling of the column. Now, I told that buckling is a very important behavior because when it comes to excessive elastic deformation, although the load which is applied is within the elastic limit, the material might still result in failure due to buckling. So, this should be treated as a very important mode of failure. The next type of failure is vibration. Now, this is a dynamic property, and in any material or material system, or you can call it a structural system, there will be vibration due to whatever loading or whatever load it is undergoing. Normally, vibration is acceptable as inevitable phenomena, but this vibration, when it reaches resonance or when there is excessive amount of vibration, then even when the load that the material undergoes is within the elastic limit, it can still attain failure. And the next common type of failure would be yielding failure. Now, failure due to yielding can be again accompanied with three different modes. One would be plastic deformation at room temperature. Second one is yield stress, and this is a very important design factor. The third one is creep at elevated temperatures. Now, Yielding is a common failure type for ductile materials, and whenever the yield stress is reached, the material is defined as it has attained failure. Now, even though the material doesn't completely tear apart, but still when it reaches the yielding stress or crosses the yielding stress value, it means that it has attained yielding failure. So, as designers and engineers, we'll have to make sure that the material which we are designing for doesn't cross the yield stress for a given load. Also, it's very important and critical to understand that yielding can also take place due to plastic deformation. Next, we'll see creep at elevated temperatures. Sometimes, even though the stress is below the yield stress, creep can be a very important factor which we have to consider. Due to elevated temperatures, even within the elastic range, the material can undergo creep, which is again a failure. We'll be looking more at creep at the end of this session. So finally, the next common factor is fracture. So again, failure due to fracture can be accompanied by different modes. The first one will be fatigue or progressive fracture. The second one is sudden fracture experienced in brittle materials. The third is going to be fracture due to stress at high temperatures, and the fourth and final will be ultimate stress, which is again an important design criteria. Now here, as for fatigue or progressive fracture, this is a fracture that takes place in ductile materials. So in ductile materials, the material will first undergo phenomenons like strain hardening, necking, and then finally move to failure, which is fracture. But when it comes to brittle materials, it is going to hold for a long time and then suddenly break, which is snap without any kind of indication. The other two, fracture due to stress at high temperatures and ultimate stress, are understandable. And now that we have talked a little about ductile and brittle materials, we will see what are ductile materials and what are brittle materials in detail. Ductile and brittle materials. Now, we've already seen a little bit about ductile materials in the previous sessions. And again, when we take the stress strain diagram for ductile materials, we can see that these materials again have a prominent elastic region and a prominent plastic region, wherein this plastic region again has yielding, strain hardening and necking. And if we see in this area, which is sigma PL, it's called the proportionality limit, after which the elastic behavior of the material comes to an end and the material slowly starts behaving like a plastic material. So after proportionality limit, we then have sigma Y, which is the yield stress. So this is the point where the material undergoes yielding, and as engineers we can already call this material going under failure. And next limit for us is the fracture stress, which is sigma F. Now sigma F can be seen below ultimate stress, and this can also be called as the region where material is definitely going to fail. And when it comes to ultimate stress, there is a sudden drop. So this is where the material snaps into halves. So basically, ultimate stress is the region where we get the failure without any indication. One thing which we have to notice within this diagram is that once the material reaches its yield stress limit, you can see that the progress of strain here is much higher than the progress of stress. But then again, when it has to reach to the ultimate stress, the value of stress keeps increasing slowly after it goes beyond the yield stress or yielding region. Now, this is exactly why whenever we use the universal testing machine or UTM, we mainly consider the ultimate tensile strength, or you can say that the ultimate stress. So with that, we'll go to the stress strain behavior of mild steel, which is basically a ductile material. Here, if you can see in this graph, this is again a strain diagram for mild steel. So like how we saw in the previous graph, important regions are given here. The first one would be our elastic region, then there will be yielding, and then there will be necking, and then there will be fracture. Here again, if you can see, sigma PL, which is the proportionality limit, comes under 240, and then sigma Y, which is our yield limit, and that comes under 262. So we can say that very small elastic strain values can be noticed when compared to its plastic behavior. So if you can see here, in the plastic behavior, it can go up to 0.380. At the same time, below the yielding limit, it is below 0.030. There is a lot of difference between the plastic and elastic region when it comes to strain. Next, sigma Y is the yield stress and is the highest stress that can be applied before yielding. Now we've already seen about this, wherein sigma Y is our yield stress. Third point, which is sigma U, that is the ultimate stress, and this is the highest stress that can be applied before necking or eventual failure. Now we have sigma U as 435, which will be our highest stress that has to be considered. Now the same way, we have a stress strain behavior of cast iron, which is a brittle material. Also, we have to keep in mind that there are some unaccounted loading conditions which we can call as impact loading. So one main example for impact loading would be natural disasters, for example earthquake or tornadoes or hurricane hitting buildings, and in these times mild steel or materials like mild steel can undergo unaccounted loading, and while undergoing unaccounted loading, this region, which is from the yield stress up to the ultimate stress, this region can help withstand the unaccounted loading. So with that, we'll go to the next material, which is cast iron, and this is a brittle material, and for this also again we'll be seeing the stress strain behavior. So when it comes to cast iron or any brittle material like cast iron, the stress strain curve is something that looks like what we can see in the right hand side. So all this time, the stress strain curves that we were seeing were loaded as tensile stress because ductile materials have very weak compressive properties. However, this material has both loads. One is the tensile and the second is the compressive load. If you can see here, it starts from the tensile load and then goes into the compressively loaded region. So we'll see that again. So in the right side, you can see there is a small curve that starts with the tensile loading, and then this curve gives you the yield stress, which is basically equal to fracture. So now that we've got the yield stress, we can say that it has reached its yielding. But we know that brittle materials do not have yielding, they just directly have fracture. That is because already we saw that brittle materials are materials that break without any indication. So here the yielding stress can actually be called as fracture stress, which finally results in the complete failure of the material. However, when it comes to compression, it is a completely different story. You can see that when compressive load is given, the graph keeps on going linearly, and then it goes approximately up to a value of 1000 until it reaches its compressive failure. Now from this graph, we can say that brittle materials are usually weaker in tension but stronger in compression compared to ductile materials. Also, in tension, the fracture is initiated at an imperfection or micro crack and the failure occurs rapidly. So like we saw earlier, the failure occurs in a snap, there is no indication. But in compression, the flaws and micro cracks basically close because we are giving inward stress and the material can withstand much higher stresses. And if we take stress strain behavior of concrete, which is again a brittle material, we can say that from the graph, the compressive strength would be up to 34.5 megapascal, and at the same time it has a very low tensile strength, which is approximately 2.76 megapascal. Now we know what a concrete is. And we also know that it can have lots of cracks or micro cracks inside, because we know that concrete is basically made of few different materials like sand, cement, and it's just a mixture of all these materials. Now these materials are mixed together and then it's solidified. These cracks and micro cracks are one of the very important reason for it to have a very low tensile stress or tensile strength. But when it comes to compressive strength, the difference is very high, and therefore concrete is widely used in many building structures. And also, to compensate for the substantially lower tensile strength of concrete, we reinforce concrete with steel rods, making it much more stronger in the tensile region as well. So now we can call concrete as a composite material, wherein the steel holds tensile strength and concrete holds the compressive strength.